So just now, before the break, we have arrived at two calculations. One is finding the anode equivalent potential equal to A equal to zero point 0.5 something, B equal to negative 0.5 something also. Next, we look at one extra theory. Extra theory. Again, I summarize the main point from the chemistry class. So now we look at the relationship between passive potential, EPP, passive potential, EPP, capital E sub PP, passive potential, corrosion potential, capital E, corrosion, CORR, corrosion rate, capital I, corrosion, critical current density, capital I, critical CRIT. So we are look at this four parameter relationship, EPP, E corrosion, I corrosion or corrosion rate, I critical, critical current density. And then I give you one chart in your tutorial handout, right? This chart. So as you can see here, this chart you have a few points, a few reasons. So this actually is an event diagram. So again, potential y value y-axis, E on y-axis, x-axis is log I. Okay. So again, don't confuse with the line here first. You clear of the axis and the axis meaning first. Y is the potential, E is the log I axis. So when you do calculation, you need to convert the log I into 10 power something. Okay. All right. For potential statics polarization curve, under chemical, when you talk about corrosion, there's one specific chart explaining about the potential static polarization. So there are three regions on the graph that you can see when you conduct experiment. So one is called transpassive region, passive region, and active region. Okay, you'll see three region or three zone: transpassive region, passive region, and active region. So this also tell you, like previously, why you see active, passive alloy, passive alloy, active alloy. So this is the region that they have identified. What are the process that going to contribute to corrosion? So we back to the four main parameter here. So on the graph here, if there's one point here, this point is called, there's just at the border between passive and active. There's one point here called critical point. Okay, this critical point, after this critical point, the voltage is going to change. Right? You see this one, initially if you're at active, your voltage is going up with a negative gradient, positive gradient. Then when you reach critical point, it becomes negative gradient already. Okay, negative gradient, and then suddenly jump up, then it go positive gradient again. So we are looking at this point, critical point, that give you corrosion potential. Not corrosion potential, is the critical current density, this one. This point, if you project down to the current axis here, you get current critical. And then from this point, you project to the left, you will get your EPP, which is the passive potential, EPP. Because this is the border, after this point, you go into passive region. So this voltage here, or potential here, we label as EPP, passive potential value. Okay, so the relationship between critical current density and the EPP, they are the same point. Y and X value, they meet at one point here. Then another Another one that we are quite familiar with is the corrosion potential and the corrosion rate. With this, we look at the active region here. We look at active region here. So it will be somewhere in the active region here. So here, let's say we pick a point here. This point will give you y and x coordinate. So your x coordinate is your I corrosion, your corrosion rate. You project to the left, you'll get your corrosion potential. Okay, so there are 2 points. We're interested in the active region here, and the value of this point and this point, we can say that they are quite close. They're quite close. Okay, so to tell the relationship between these 4 parameter, we use back the TEFL equation, right? Over potential equal to A plus B log I. That what we learned before this when we derived the equation in the previous lecture. So on the left hand side, this nu equal to over potential of anodic reaction. Why anodic? Because TEFL equation, they are more interested in the corrosion rate, in the corrosion member. Okay, so that's why this one on the left hand side is the over potential voltage that trigger the corrosion reaction. Okay, anodic. Then B is the anodic TEFL constant. Okay, put back the equation that we learned. All right, so we have 2 points. Right, we have 2 points just now. 1 point is corrosion point. 1 point is the passive potential point. Still remember, we have two points here, 1 and 2, right? So when we put the point into the TEFL equation, so you still remember on the left hand side, this one is the voltage potential. So how you find the potential? You take the E corrosion minus the equivalent of A. With this, you take the value of this one and then minus the potential of that that element. Okay, E corrosion minus the equivalent potential of A equal to A plus B log, this is a TEFL equation, and then the I, we use the I corrosion because E corrosion is the E corrosion partner with I corrosion, right? From the chart, right? E corrosion partner with I corrosion, the corrosion rate. So that's why the first equation here, it combine the first point, E corrosion. I mean the TEFL over potential here is before this, we see a graph called IR, where you take the potential minus the corrosion potential, the standard potential, right? So you get the first equation. You do the same for second point, where you substitute, the next one, you take the passive potential minus the equivalent of the A standard potential. And then A, you continue to use. B, you continue to use. Log I here, you use the I critical. You combine the point, the second equation, you combine the point. So you have two point here, two equation here, 1 and 2. What you do is that you can do simple more mathematics strategy where you want to find the relationship between these 4, right? What you can do from the 2 calculation, you combine both equation. How you combine? You take 2 minus 1. Equation 2 minus 1, you want to eliminate A. You want to eliminate A, you want to eliminate the equivalent standard equivalent potential. So you take 2 minus A, 2 minus 1, what happened to this one? This one minus minus become positive, cancel. A minus A cancel. So EPP minus E corrosion, you get this one. BA log, again, you just see this one as log minus log, right? Log minus log, so you have BA log something minus BA log something. So you factor them, BA log I critical minus log I corrosion. You get this equation, right? Then you apply the understanding in log. Log minus log is divide. Log minus log is divide. Log plus log is multiplication. All right. You simplify the log. Log minus log become log. This one divide by this one. All right. This is what you learned in your mathematics, right? Okay. So we arrive at one equation. So this equation, it links these four parameter together. EPP minus E corrosion, a constant value of A, a constant value of B is a TEFL constant, log I critical and I corrosion. Okay, copy this one somewhere in your notes because you're going to use this one to solve the question. Yeah? Okay, copy this one. EPP equal to E corrosion equal to BA bracket log I critical I corrosion or critical or corrosion rate, critical corrosion rate. Okay, this process, this equation, we are looking at active region of the event diagram. Next, we move back to our question. So we have clear A. We have clear. Okay, let's see. Okay, we still have A, but the second one. We want to find the corrosion current and potential for metal A. So again, anodic polarization and cathodic polarization. Just now, before break, we look at finding the standard potential, Catholic standard potential, and anode equivalent potential. Now we look at polarization. So polarization for A, metal A, we have two, anodic polarization and Catholic polarization. So anodic polarization, just now I explained about this equation. Right, I explained about the EPP, E corrosion, BA, why you can get the log something divided by something, right? So this one is for the anodic polarization. You substitute the value into the equation that we derived just now. So EPP equal to E corrosion A. This one equal to minus 0.523. Why minus 0.523? Where can you find this one? Just now you already find for A, right? The anodic equivalent potential you find is minus 0.23 volt, right? You use this value as E corrosion here. Sorry. Let me see here. I think I have moved something. This one I maintain. This one is equivalent potential. Passive potential. Minus. Okay. Yeah, there are some mathematics rearrangement here. We want to find the potential corrosion for A. So we just modify a little bit. So what we do here is that we play with the mathematics sign here. So negative, sorry. let me see how. You have the whole equation to have a negative value. As you can see here, BA is 0.1 because just now it tell you the Tefel constant is plus minus 0.1. So we use 0.1. Log I critical means we flip the whole equation. Why we can flip the whole equation? You can see here corrosion A, because in the previous equation here is this one divided by this one, right? And then we want to find the corrosion, right? So we just rearrange the equation, become E corrosion in the front, and then this one you change sign. Basically, you can substitute the value, then you rearrange back, you still get the same structure. But we write in a certain way that presentation of E corrosion minus the EPP equal to 0.1 log, then this one below, then this one above. Basically, you rewrite this equation. We want to find the positive E corrosion. So what you do, you move this one to left hand side, move this one to move the one to right hand side, move the one to right hand side, pull the whole thing to left hand side. That's why you get this one will switch place. Okay. We just play around with the position of the equation here. We didn't change. We didn't change the equation. We didn't do anything about the equation stability. Yeah. We just change the position because we want to find the E corrosion here. That's why you move around the equation, and then we arrive from this what we found just now into this form, where we focus on E corrosion A. I hope you can see the mathematics procedure we have here. Actually, it's the same thing. It's just that we rearrange the equation. Okay, so we get E corrosion A minus something, log something, and so on. You do the same for cathodic. So cathodic, you use the same procedure, right? You use the same procedure. So your EPP is 0 because before you couple, you get 0. Okay, before you couple, you get 0 here. Then the rest is same. Only the I corrode here is 4. Yeah, here. Okay. I corrode. No, I corrode. I critical. Sorry. I critical for Catholic is 4. Then this one is 2 point something. I hope you can see the differences between anode and cathode value here. For Catholic, we use the hydrogen evolution value. Catholic polarization. Why we use the hydrogen evolution current? Still go back to the foundation. When two metals meet together, they fight for nobility. Higher nobility go up. This one sacrifice himself, contribute electron. This one became cathode, right? So cathode, on the surface, you have negative charge. So negative charge, what the negative charge do? Attract positive charge around it. In this case, we assume acidic lah. So when acidic, H positive charge will attract to the cathode, right? So here you have hydrogen created in the high nobility metal. So here you have the hydrogen evolution happen on the surface here. So that's why for Catholic polarization, you are using hydrogen evolution value here and not the corrosion value for I. Okay. Okay. I hope you can see the differences. This I naught I not HA and IHA. There's a difference between this one knot and one without knot. If you look back at the question, hydrogen evolution is this value, and exchange density current is this one. So from the sample answer here, you can see that how we use Tafel equation in analysis. So from here, we calculate the anodic polarization, cathodic polarization for A. We have two equations here. All right, we have two equations here. Okay. Okay. Again, there's a negative sign for cathodic polarization. This is part of the special things when you do cathodic. Anodic, you don't have. Anodic, you have a positive value of B. This one, the Tafel constant. You have anodic positive. You still remember when you plot the graph, right? What happened to the anodic line? Anodic line, positive line, right? The line for the anodic on the even diagram? When you plot anodic, what happened? The line go positive gradient, right? What happened to the cathode? What happened to the high nobility metal line? Negative line, right? That's why one positive, one negative. Yeah, I hope you can link what you learned before this in this question. Positive. Why this one positive? Because in the Tafel or in the even diagram, when you draw the line of the less nobility metals, it's always go up, right? Positive. But when you draw the line for high nobility, there's a negative. Sorry, there's a negative gradient line on the graph. So we have two equations here. You have two equation, two unknown. It's like you have the x, you have the y and x, two equation you can solve, right? It's a linear simultaneous equation. So solve these two equation, but you just treat it as a linear equation. Y, x, you have two unknown, solve two equations simultaneously. Okay, I give you the answer. You'll get that the E corrosion A equal to this one, minus 0.148 volt. I, or corrosion rate for A, is 0.21 negative 4 ampere per cm square. You get this two value after you solve these two. Copy this one. Okay, so at this moment we solve for metal A. Okay, copy these two. Okay, I move on. What happened to B? You do the same procedure, right? If you understand A, you do the same procedure by replacing the value inside here. All right. So B also have anodic cathodic process using the same equation. All right. So your EPP you already calculated, minus 0.531 volt for B. You substitute here. Y anodic again. YB anodic is positive. On even graph, when you plot the graph, the line for less nobility metal go up, right? So positive 0.1. How you get 0.1? The question will give you plus minus 1 Tafel constant, which is the one that you draw on either diagram. Less nobility for anodic process go up. High nobility negative. That's why you get negative 1. Then the rest you just substitute accordingly. right? For anodic, you use the corrosion current, density current. Is it current? For Catholic polarization, you use the hydrogen evolution. The I for the hydrogen evolution. Okay. Again, two equation, two simultaneous two unknown here. This one and this one. So two unknown, two equation you can solve one, right? So just again assume this one as y, this one as x. Y and x, you have two equation. Solve the simultaneous. I give you the answer. So the potential for B, potential corrosion for B is minus 0.25 volt. Corrosion rate for B is very small, 3.1 something, 10 power negative 4 ampere over cm square. Okay, copy this too. The rest is substitution. Then this one just a cross check of for your revision. Okay. Potential corrosion for B is minus 0.25 volt. Corrosion rate for B is 3.16 negative 4 ampere over cm square. Okay. All right. So again, I already explained why positive, why negative. Why anode use positive, why cathode use negative. Okay. We have done for section A when both A and B are not joined together. So we define the corrosion current and corrosion potential. Okay, corrosion current, I current, and potential, corrosion potential, E corrosion. Okay, we define the corrosion current there. Okay. We move to a new case here. We move to a new case where we have B, where two metal join together. What happens when two metal join together? Okay. When two metal join together, again, you need to change the constant inside there. Right. The one that you see here is before they join together. Section B, when they join together, galvanic process happen. So we will use mixed potential theory, total oxidation rate A and B equal to the total reduction rate. This is the main key that we will use to solve for scenario B when they join together. We look at total oxidation rate of A and B equal to the total reduction rate. So total coupled cathode exchange current density, we will combine the exchange current density of A and B for coupled scenario. So in equation, when you combine two metal together, you will use this equation where you look at the current of a coupled. O means standard, right? O means standard equal to A plus B. Okay, equal to IH A plus IHB with a hydrogen evolution of A plus hydrogen evolution of B. Then you substitute the value. What happens if you couple the total density current that you get is you combine A and B. What is the value for hydrogen evolution for A? Is 4. What is the value for hydrogen evolution for B? Is 1. Both is 10 power negative 6, so you just combine 4 plus 1, you get 5. Copy the 10 power negative 6. Unit is ampere over cm square. You get the first setting for coupled scenario, where you calculate the I coupled, the exchange current density. Right. The information given in the question actually is separate, A and B, but you need to smart enough to combine the information when they coupled. So when they coupled, you use I not no more individual, but you combine them together. So we have got one value. Okay, I put over here. Yeah, put over here. This one is when coupled. So all this value is when they are individual, when they split to themselves. So this line to here is when they are individual. This one is when they start to join together. You get the first value, 5 point something, 5 10 power negative 6 ampere over cm square. Next, we look at cathode and anode polarization. Still the same. We look at cathodic. Okay, we look at cathodic. Use back the same understanding in the section A. Again, I highlight why the constant Teffer constant is negative for Catholic, because Catholic is always higher nobility, and we draw line in the E versus log I graph. It's always negative. Sorry, on your line on your side is okay. I confused the direction on the green screen, but anyway, negative means it's a negative gradient on the E versus log I. Okay. So you substitute the value accordingly. E corrosion coupled equal to 0, equal to negative 0.1 log. I corrode coupled and I not coupled. Okay. So, okay, why the potential is 0 for cathode? Because nothing happened to higher nobility at the cathode higher nobility. Nothing happened to that individual, right? He just lie there and receive electron. Nothing happened to the potential, right? So passive potential here is 0. Then you rearrange. You substitute the 5 combined density current just now. You get one equation. Okay, you get one equation. Then we look at anode polarization. Okay, something happened when you combine together. The low nobility will corrode itself. So we need to pay attention to anodic polarization. Okay, anodic polarization, same, but now you use this equation, Teffer equation. So Teffer equation equal to equivalent minus A minus B equal to log 1 log I, B, and 5. This is the total current density, but now you want to find the B. Why B here? Because in the beginning we already know A, B meet together, which one is higher? A higher, B lower, right? A higher than B, right? So B corrode. So corrode one will become anode. So you use the density current for B over here because you're looking at anode polarization. Okay. The rest you can read. You just substitute what is the A equivalent We calculate just now. Minus the B equal to log I log IB. Okay. So this equation, you can calculate only one unknown here. So your IB equal to 6 10 power negative 7 ampere over cm square. Actually, you can remove the over voltage here. All right. You can remove this one. Okay, you already get the second parameter, IB, by substituting the equivalent of A, equivalent of B in the equation. Okay, so I pull this value on the right hand side. I put it here. I corrode B equal to 6 point something, 10 power negative 7. And total anodic current coupled at minus 0.23. It is this one. So you can use this equation. I total of A, total anodic current for A equal to I naught A plus I naught B. You already calculated for I naught A just now. Okay, I naught A is 2. This is given in the question. Plus the IB. Just now you calculate. You'll get the total anodic current when it coupled at this voltage. This voltage is referring to A. Your current that happened at A will be 6.22 10 negative 7 ampere over cm square. Recall back this equation, anodic polarization line. You have E corrosion coupled minus the EA log 1 anodic. Again, Y positive 0.1 because anodic go up positive line. Log I corrode divided by ITA. Because now you already coupled the two things together. Substitute the value. This one over here. EA given you already calculated in section A. Right, this one is for anodic polarization. So this is what we arrived just now. Anodic polarization give you this equation. Then Catholic give you this equation. You do the same calculation. So Catholic, just now we found this equation. 0.1 here. So you have two equations here. Again, you are finding yx. You have two unknown. Solve the unknown. You'll get E coupled equal to minus 0.2 volt. Corrosion rate will be 7 10 negative 4 ampere over cm square. Okay. Copy this one as your answer. Okay. The process will repeat All right, we keep looking at anodic and cathodic process. We solve for the unknown, then we'll get the E and corrosion coupled. Yeah? Okay, we go for a few more slides. Yeah? So this is a slide that I include in your tutorial handout. This is a galvanic coupling between two corroding metals. So we have all the points lah. Okay, this basically is a event diagram. So voltage versus currency. So you refer lah to each of the P or Q dissolution, H evolution, total deoxidization, and total reduction. Okay, it will take some time to understand, but anyway, positive one. Let me go here. Okay, positive line on the event diagram. The positive line, you know that it is anodic. When two metal meet together, anodic, cathodic. This is anodic. This is cathodic. Right? This line represent contribution of electron. This one also. Then the rest still same. That's why this give you the positive Tefel constant just now. Why sometimes you use positive 0.1, why you use negative 0.1. This is what I mean just now. Okay, this one, your homework, go and study this graph. Okay, you substituting the E corrosion for, okay, now we are looking at the section C. We look at galvanic corrosion rate of the metal at the corrode at a higher rate. So we substitute the E corrosion rate couple as this one into these two equations here. You substitute this one inside here, this one inside here. Okay. So you have, before you substitute, you have two metals, two anodic process, right? You have metal A, metal B. Anodic polarization, you have one equation for A. Anodic polarization B, you have one equation for B, right? Just now in the section A, you calculate A and B. So this is the A1, this is the B1. So you can estimate the corrosion rate of A and B after coupling by using this equation. E corrode equal to minus 0.523 equal to log 1 corrosion of A to B. And another one, you can use the same equation, but you change the corrosion of A minus B. This one is more focused on B. This equation is more focused on B. This equation is more focused on A by looking at the value in the equation. Okay, this slide shows you that you're focusing on anodic polarization for A and B. This one you already derived in A, in section A. You apply what you learned in A, you calculate the coupling process. All right, you just modify the equation a little bit. This one is individual. What happens if you combine? So you change this equation become A combined with B. This one you change also B. A combined with B, but this one focus on B. This one focus on A. Okay. Since you have two equations there, same unknown, right? So you can find, right? Two equation. This one is the same. So you are using the E corrosion coupled here. substitute this one here, substitute this one here. You have two equations with two unknown. Solve simultaneous equation. You can find the corrosion rate A to B is 2 point something when you focus on A. And you solve for A corrosion AB. This one is focused on B. Corrosion rate for B will be 7 point something 10 power negative 5 ampere over cm square. I hope you can tell the difference. These two, although the label is AB, but I highlight the A, I highlight the B. So this one is the corrosion rate for A. If you join AB together, A will corrode at this one, B will corrode at this rate. Both will also corrode, but one is faster, one is slower. Okay, so in here, which one is faster, which one slower? This value higher, right? So B will corrode faster than A, which agree with our assumption. Because A is high nobility, B is low nobility. Both if corrode same time because of the galvanic process, B will corrode faster because B is at the lower level of the nobility. That's why in this here, the calculation agree with the assumption or agree with the potential standard potential nobility chart. Yeah. So this also tell you what happen if you combine two metal. You can find which one is corrode higher. Okay. Okay. So here it tell you that B corrode faster lah. Okay, so this is C. We go for the last slides. What happens if you increase the concentration of your A? So just recall before you coupled, what happened? Before A and B coupled means you separate, the cathode is 0 volt because there's no connection. So your cathode will be 0. But anode for A will give you this equation. This one you have seen in the section A just now. It's just that you substitute your concentration become 1. Okay, concentration become 1. This one same. This is 2, but log concentration now. Just now you use 3 point something for the log, but now the question asks you what happened if you increase the molar, the concentration become 1. That's why here it changed to 1. You substitute this value, this one was given, you calculate, you'll get minus 0.3 volt on anode. So next thing you look at is the anode potential polarization curve and cathode polarization curve. You substitute the same equation, but you modify a little bit. Here, you look at the equivalent of A change already. Change value to minus 0.36. So you substitute minus 0.36 here. The rest will be the same. Still 0.1, still 2.1, still same. But what you change is the standard potential equivalent at the anode change already. So at cathode polarization, there's no voltage happen. All right. So you have two equation again. You have two equation again. You have one unknown, two unknown, same. Two equation, two unknown, you can solve. Simultaneous equation. Treat this one as y, this one as x. Here also y, this one as x. Solve the equation. Again, I highlight why for cathode y there's the Teffer constant is negative. Because cathode is negative gradient on the graph. Okay, you solve, you get two answers. Corrosion of A, potential corrosion for A equal to negative 0.06 volt. Corrosion rate for A will be 0.83, then negative 5 ampere over cm square. Okay, so compare this answer D with section B. What happened to the corrosion if you increase the A? Side by side, you can see okay, you calculate this one in B section. This is what you calculate in B section. The corrosion rate you calculate just now when you coupled with the 310 negative 6 molar, your corrosion rate is 1.2, 10 negative 4. But when you increase the molar, increase the concentration, A become more A component. Again, A is a higher nobility. What happened to the corrosion rate? Does it increase or drop? Just look at the slide here. All right. One is negative 4, one is negative 5. From this calculation, what does it tell you the effect of increasing the high nobility metal in the concentration? Does it increase or decrease? Okay, before we go, I ask one question. Rogeswaran, are you there?
Yes, sir.
Okay, Rogeswaran, you look at the slide here. Just look at the numbers. Initial condition, you have less A. Then after the section D, you increase the A element in the solution, become 1 mole. What happened to the corrosion rate? What can you observe here? Does it increase or reduce? Does the corrosion rate increase or reduce?
Reduce, sir.
Reduce, So this is also one of the way you control corrosion in galvanic. What happened to the potential? Can you see? The potential of corrosion before, after you increase the corrosion. Minus 14 volt become minus 0.06. What happened to the voltage? Does it increase or decrease?
It decrease. I mean, increase. Increase.
Increase. So yeah. So when you come to a higher level module, try to get some idea on the negative side, right? What happened, right? Which is more positive or more negative? So the voltage reduced. So from here, you can see high nobility, no low nobility. Corrosion happen when you have a difference of nobility. If you increase further the concentration of the higher nobility, you can control the corrosion. Okay, the concentration you increase, you can control the galvanic corrosion from this example. Okay. All right, so this one you can read lah. Okay. You do another set for the calculation. I'll just put on a slide here. You go through my PowerPoint slides, all right? So when A and B coupled, you get this one, and so on. You get your IB there. So this just to check what happened to your current to your B. You can read all my slides. I haven't got through again. The procedure still same. I will show you the final. Still same, right? You will get equation and then you solve simultaneous equation. Then you get the corrosion when you coupled, current when you coupled. This one for the D section. Okay, for the D section. Okay, I will conclude this chapter 5 today. So we will start chapter 6 next week. Okay. Okay, let me end the recording.